So in this example, they both have a speed of 3 meters per second and are rolling at the bottom of the ramp. The ramp has sufficient friction for them to not slide or slip. Can you figure out how far along the ramp they travel until they stop and then roll back down? So I'm looking for kind of where they come to rest before rolling back down the ramp. You guys do this for both the ring and the disc? Give it a try. Work together, it's not a quiz. This is the opposite of what we did last week. I want to see if you can prove something. So 1.8 meters and 1.35 meters. Well, that's what we should be looking at. So if you're having trouble, some of you got 0.9 and 0.675? Well, the reason why you have that is because you found the height. You didn't find the length along the ramp. So I wanted the length along the ramp. Now, to get the length along the ramp, you're probably going to have a point in your work where you're going to be getting the height. But that's not what I asked for. I want the length along the ramp. So I have a few of you who couldn't do it or had some interesting arithmetic. So let's consider the arithmetic. We'll start with 1/2 mv squared plus 1/2 I omega squared. Does that make sense? This is the amount of energy that we have at the bottom because we are both moving from one place to another but also spinning at the same time. This equals mgh. Now, this will get you h, but in order to do so, you're going to have to either put it all in terms of the angular speed or all in the terms of the linear speed. I think a lot of you decided to put it all in the terms of the linear speed, which makes perfect sense. So 1/2 mv squared plus 1/2. And I'm going to just put parentheses here because this part is the same whether we're dealing with the disk or dealing with the ring. And what you do now will depend on whether you want to solve this for the ring or solve this for the disk. So if you're going to solve this for the ring, you're putting in mr squared. And if you're solving it for the disk, you're putting in 1/2 mr squared. Now, it does give you two different things, obviously. So if we do the ring, the r squareds cancel, and we just get 1/2 mv squared plus 1/2 mv squared equals mgh. If you do this for the ring, for the disk, you get 1/2 mv squared plus 1/4 mv squared equals mgh. Now that gets you your two values for h, but that's not what I asked. So are there any questions about those things? All right. Something important. I never said they were the same size. I never said they were the same mass. We've been trying to compare things that are the same, clearly, so we can see what is different. But please notice the mass and the radius didn't matter. So this could be a little tiny ring and a really big disk, and they'd still behave this way. And you should be able to explain a little bit as to why. I think there's two things, if you're asking why, that you should be able to say. One of them is the same thing that causes their inertia, mass, is also the same thing that's being used to slow them down, mg. Right? So the force acting on them is based on the mass, and the translational energy they have is based on the mass. That's why the mass doesn't seem to matter. Now, the R, well, that's because the frictional force acts at the edge, and if it's a bigger disk, you'll have a bigger torque. A smaller disk would have a smaller torque, but a smaller disk would also take less torque to stop than a bigger disk, which is why the radius seems to not be as necessary. But keep in mind, if they're the same size, which one has more energy at the bottom? You'd be able to answer this one. Do we not have it? I've heard a few people whisper something. The ring will have more energy at the bottom if they are the same sized object. And it should be clear. When you add those two things up, you have more energy if it's a ring than it's a disk. That is why the ring will be higher up than the disk. Now, one last thing. H does equal L sine theta. That's how you get the length along the ramp. And since sine of 30 is a half, you're dividing 0.9 by a half to get 1.8, and you're dividing 0.675 by a half to get 1.35. That's where the answers come from. One more thing before we leave this. There's a moment when the disc and the ring are both on the ramp. I'm going to ask a question that I think is challenging, but before I do, can you just take a shot at drawing the forces that act on the disc as it's traveling up the ramp? Assume it still has a velocity in this direction and is still rolling. What would be the arrangement of the forces on the object? Please don't draw them all at the center of mass. We know that at this point, for something that's spinning, we should be drawing the forces at the point of application, where the force is applied. You guys got the easy one, sure. Almost everybody, without fail, drew a downward arrow for friction, or for the weight. Good job, that's great. Many of you made sure that your normal force was drawn correctly. And on a test, this is going to be critical, just so you guys know. Starting at the point of application, being drawn through the center. Normal force, that's my expectation. It should be drawn carefully. Using a ruler will be best on the test. I would say that we're batting less than 50% though for friction. So take a look at your answer. Friction is what's causing the angular speed to change. Is the angular speed getting bigger or smaller? Sorry, say that again. Is the angular speed getting faster or slower? Slower. So I would expect the angular speed is becoming a smaller number. That has to come because there's an unbalanced torque acting on it. If it's spinning this direction, what direction would friction try to prevent that? It's not going to be down the ramp, that's for sure. It's going to have to be up the ramp, this way. That has to be the direction of friction, to try and prevent it from rolling up the ramp. It's slowing it down. When you're deciding what direction to draw the frictional force from now on for things that spin, it's about how the angular speed is changing. So in this case, the friction has to be up the ramp. So we're pretty comfortable with this arrangement, and we figured out where our issues are. We can handle it. So I want to change this just a little bit. Let's get all this stuff out of here. What I'm going to do is I want to replace the ramp with a different ramp. So this ramp is similar, has same angle and everything, so it's still 30 degrees. But this ramp has a coefficient of friction that is nearly zero. Okay, so it's a very smooth ramp. The objects are still being started at the same speed. Can you figure out how high along the ramp these go? In fact, what I would want to know is, do they go higher, less high, or the same? And if it's different than before, find L again. But think about how this situation is different than what we just did. So again, it's less for both. And they, although get to the same height, they're going to be less than they were the last time.
but they'll both go to the same height because in this case, the rotational inertia doesn't really make any impact. Now, I did see some things out there that I think are wrong. So let me highlight them. The amount of energy that both of them have before they start is still different because they both still have rotational kinetic energy. So they have different energies. The difference is, if we say pick one of these, the disk, and talk about it. When the disk makes it up here, although its velocity will eventually zero, its angular velocity will be unchanged. There's no frictional force to cause a change in the angular velocity. So when it makes it up to its maximum height, it's still spinning. So it still has kinetic energy. And that's why. Any question about that? Okay. One final thing I want to speak to, and then we'll be done with this example, I think. And there's other versions of this problem. I'm just trying to give us a overview of these kinds of questions. Let's go back to the other ramp for just a minute. Okay, so we're looking back at the same ramp that we had at the beginning, which has a coefficient of friction that is not zero and is enough to keep the objects rolling the whole time. And consider the point where we're still making our way to the highest point. That's no longer true, but we have both of these guys. We already are pretty aware that the ring will make it to a higher location than the disk, as long as it's rolling the whole time. Now, you guys would, I think, feel pretty confident that we know how the forces are working, that there's going to be a weight acting on the disk, a normal force acting on the disk, and friction acting on the disk. Now, those forces are going to be largely the same. Since these guys have the same mass, and are on this ramp in the same way, we know those two forces have to be the same. Will friction be the same for both? If I was asking a test question, this would be the one I'd really want to hear your answer to. And there's a number of ways to attack this question, but I want you to think about whether friction would be the same or different. If they're different, which one would have a larger frictional force? If they're the same, okay, then you think they're the same. But be able to describe why you think that is. Take a few minutes and talk it out, and then we'll come back and see if we can't come up with a consensus. Look, I know a lot of you are unwilling to take a stand on stuff like this, but it's science. So there's a right answer and a wrong answer. And we don't have it, although there are things in science that are ambiguous, this isn't it. Right, there's a right answer here. And the argument that you made referenced this relationship. It's a good reference to make. There's a problem with this, though, and it's subtle. The biggest problem with this is that what type of friction are we talking about? Kinetic friction or static friction? Static friction, right? The point's not actually sliding. So the actual formula that we would be using is an inequality, right? That's important because that means that the frictional force is any value between 0 and the maximum, which means there's no reason to believe they have to have the same frictional force. But there's other arguments to make, like what if the materials are the same and the angle is the same? These are all things that we would think would contribute to that. The normal force is the same for both. So we know that for both of them, normal is going to equal mg cosine theta. So when we plug that in, that's still going to be mu times mg cosine theta. But it's less than or equal to. So let's see if there's another argument to help solidify our case. and this is a little more technical, but I need you to know this. If we were doing the translational work here, meaning we were going to be calculating, say, the acceleration, you know that to do that, we would start with net force equals ma. We'd break all the forces up into their direction. We would take the mg sine theta, or the mg, and break it up into mg sine theta and mg cosine theta. We would choose a coordinate system that makes sense. Something like this. I'd probably say something to you like, do you want to make up the ramp positive or down the ramp positive? We have to make a decision. So up the ramp is positive. That's fine. That means that the velocities are positive when we first start out. That make okay sense? Help me out here then. If we do that, then is the acceleration positive or is the acceleration negative? It would have to be down the ramp, correct? The velocity is in the positive direction. The acceleration is trying to slow the object down. So the acceleration that the objects experience has to be this way. Right? That has to be the acceleration direction. So if we're going to make up the ramp positive, that's fine. But the acceleration is going to be negative. It's going to be a negative number. Are we all okay with that argument? There are two forces acting along the x direction. One of them is friction. It's positive. The other one is mg sine theta. And that's clearly down the ramp the other direction, so that's minus mg sine theta. And that has to equal ma, but this will be negative. That means this number is going to be bigger than this number. It's the only way that can be negative, right? So let's think about the the disk and the ring. Which one has a bigger acceleration down the ramp? The disk or the ring? Which one slows down first? The disk slows down first. So it must experience a bigger acceleration. Right? Now, we are taking a positive number and adding it to a negative number. Can you wrap your brain around this? If I want to get a bigger acceleration, that's negative. But I want to make sure what I add is less, right? I want to add less to it. Are you able to do that in your head? Can you work that, or do you want to put some numbers here just to hold a place in here? Let's imagine that the disk is got an acceleration that's bigger. The disk has a bigger acceleration than the ring because it goes farther. So let's just say the disk is got an acceleration of 1. And let's say the ring has an acceleration of 2. If this were 3, right, it has to be bigger. And that part's the same for both the disk and the ring. To make 1, I have to add positive 2, right? And to make 2, I have to add positive 1. So if this one goes with the ring, because it goes farther, and this one goes with the disk, do you see that I would have to add a bigger positive number to reduce the acceleration than the disk, so that the ring experiences a bigger frictional force? That's all there is to it. Now, there's an easier way to say all that, and we'll talk about that, I guess, tomorrow.